I welcome you all students to a session on ethers. In this session, I will be discussing some important questions on ethers. Ethers, as you all know, can be prepared readily by dehydration of alcohols using a few drops of concentrated sulfuric acid. But remember, this method is good for symmetrical ethers of the type ROR, where the two alkyl groups are same. When you want to prepare unsymmetrical ethers like R-OR, where the two alkyl groups are different, Williamson's synthesis is a better method. Now, Williamson's synthesis uses an alkyl halide and alkoxide for the preparation of ether. One of the alkyl groups can be taken as alkyl halide and the other alkyl group can be taken as the alkoxide. These two react to form, see, I will show in a simple way like this. This NaI if you remove, you are left with R-OR. Okay, you should not write R-RO. See, it is R-OR. Now, this is good for the preparation of symmetrical unsymmetrical ethers. But the question will be not to explain Williamson synthesis, which will be a straight question. I am going to give the question in a different way. To get an unsymmetrical ether by Williamson synthesis, the alkyl halide must always be primary. Why? That is the statement for which you have to give the reason. Now, for Williamson's synthesis to prepare an ether, you need an alkyl halide and an alkoxide. The statement says that the alkyl halide must always be primary. Let me take a specific example of an unsymmetrical ether. The unsymmetrical ether is tertiary butyl ethyl ether. One alkyl group that is attached to the oxygen is the tertiary butyl group and the other alkyl group is ethyl group. So this is an unsymmetrical ether called tertiary butyl ethyl ether is the common name for that. By the way, can you write the IUPAC name for this? Please write it. Anyway, I am not going to give the name now. I will be giving it to you at the end of the session. Let me write the reactants to get this ether. I will take sodium ethoxide to get the ethyl group and I will take the tertiary butyl iodide to get the tertiary butyl group. So this is one set of reactants. Can you write the other set of reactants? Please go ahead and write. And whenever I ask you to write something, pause here and then write it on a piece of paper. Please always keep a notebook by your side and write whatever you are required to write. That is the way to take advantage of the class. There is no use in going on listening to the video. Is that clear? And when you write, it will be like this. The other set of reactants will be CH3, CH2, I, and it will be sodium butoxide. What does the statement say? It says that the alkyl halide must be primary. That means this is the correct set of reactants. This is not the one. Let me explain to you why the first set of reactants is not the appropriate reactants to be taken for the preparation of this ether. This is a tertiary alkyl halide. When you react these two, sodium ethoxide will readily give you the sodium, the ethoxide ion. It will give you the ethoxide ion, which is a strong base. In the presence of a strong base, an alkyl halide, particularly the tertiary and the secondary, will undergo elimination reaction to form an alkene. So there will be a competition between the nucleophilic substitution reaction which is supposed to take place And the elimination reaction is preferred over the substitution reaction when the alkyl halide is a tertiary or a secondary one. I will show you the elimination reaction here. So when this tertiary butyl iodide in the presence of a base ethoxide ion here will pick up, see this iodine here will pick up hydrogen from the beta carbon atom. There are 3 beta carbon atoms, that is the carbon atoms attached to this carbon atom, that is the adjacent carbon atoms. It will pick up a hydrogen from one of the beta carbon atoms and leave as hydrogen iodide, that will be removed, and you have here butene as the product. So the reaction will go in a different direction to give you butene as a product, not the required ether. I suppose it is clear to you. When the alkyl halide is not primary but a secondary or a tertiary one, in the presence of the alkoxide ion provided by the other reactant, this will undergo elimination reaction in preference over the nucleophilic substitution reaction, the product being an alkene instead of ether. I told you all this to make you understand. You need not write everything in the answer. I will show you the brief answer now. When the alkyl halide is secondary or tertiary, elimination reaction is preferred over substitution and the product would be an alkene instead of ether. So this will be a crisp answer for the question. All the rest are only by way of explanation. Let me continue to say one more thing here, that when the alkyl halide is primary, as per the statement, what will happen is the reaction will be an SN2 reaction. Williamson synthesis will be taking place by SN2 mechanism, in which the butoxide ion, which is the nucleophile, will attack the halogen carrying carbon. This carbon carrying the iodine here will be attacked by the butoxide ion from the rear, and the iodine will be replaced by the butoxide group to give the tertiary butyl ethyl ether. The second question is, for the preparation of methoxybenzene, how would you select your reactants and also give reason for your answer? Methoxybenzene is this. It is also called anisole, common name anisole. In this ether, one alkyl group is a methyl group, the other one is an aryl group, that is the phenyl group. To get this by Williamson synthesis, we can take sodium phenoxide and methyl iodide. It is Williamson's synthesis. You know, to get unsymmetrical ethers, that is the best method. There is another set of reactants possible to get the same compound. I can take iodobenzene and sodium methoxide. Out of the two, which one is the correct set of reactants that you have to choose to bring about Williamson's synthesis? That is the question. Please think here and find out what is the factor that you have to consider. If we have to get methoxybenzene from this set of compounds, I have to break the bond between C and I here and O and Na here. Breaking the Ci bond is simple enough, you know, it can readily be broken. Here, ONA also does not pose much of a problem. Na can readily leave as Na+. Here, in this set of reactants, you have to break the bond between ONA in the sodium methoxide, and you have to break the bond between C and I in iodobenzene. Now, can you say which is more difficult? Breaking the ONA bond in both compounds is not very difficult. It's the Ci bond that you have to consider. Which Ci bond is easier to break? Is it in methyl iodide or iodobenzene? It is iodobenzene. Already we have discussed this as a reasoning question in one of my earlier sessions. And you also know the answer for that. Here the iodine has 3 lone pairs of electrons, and due to resonance, one of the electron pairs tends to flow into the benzene ring, giving a partial double bond character to the Ci bond here. So it is not easy to break. Hence, the first set of reactants is the correct one for getting the compound. You can also say here as the reason, iodine is attached to sp2 hybridized carbon in iodobenzene, and that tries to withdraw the electron pair from the iodine, and hence the iodine is held more tightly to the benzene ring, cannot be easily taken away. Is that clear? So you can write the answer in one of the ways. I have already given statement for the reason in my earlier session. So it should not be difficult for you to give reason for this question. Reason is the same as the for the earlier one. That is, why can't chlorobenzene be readily hydrolyzed? Here, carbon and iodine bond cannot be broken easily. That is how you have to say. Is that clear? So anyway, I will give this statement for you. I have given the answer here in terms of resonance effect, and I have also given you another reason. If you prefer that, you can write the answer that way. The third question is, when tertiary butyl methyl ether reacts with HI, the products are always tertiary butyl iodide and methanol, and not tertiary butyl alcohol and methyl iodide. The statement may appear difficult to you, but if you write the correct structure of tertiary butyl methyl ether, you will get some clarity in your thinking. This is tertiary butyl methyl ether. We are considering the reaction with HI. This is a very important reaction of ethers. Here, one of the bonds gets cleaved here, so it is called the cleavage reaction also. Now, HI supplies a proton which gets attached to the ether using the lone pair of electrons on oxygen, and so this oxygen gets a positive charge. So this is an oxonium ion now. Now this is the pair of electrons which is used. It has another pair of electrons here. So this is an oxonium ion. Now you can cleave the bond here, break the bond here. Let us call it the first option. When we cut this bond here between the oxygen and the tertiary butyl group, let us see what products will be formed. One product will be methanol, this part of it, and this part of it will form the tertiary butyl carbocation. And later, of course, the iodide will join that and will form the tertiary butyl iodide. There is another possibility also. Instead of that, this bond can also be broken. Instead of this, this can be broken. We will call it the second option. In this case, this part will be a full alcohol. So you will get tertiary butyl alcohol and methyl carbocation. See, the reaction proceeds through protonation, and cleavage of the molecule and carbocation formation. Obviously, out of the two carbocations, which is more stable, that is what should be the point of consideration here. Out of these two carbocations, you know that a tertiary butyl carbocation is more stable. Hence, naturally, the choice must be only this. And when this is the choice, your products will be methanol and tertiary butyl iodide. That is what is given. Tertiary butyl iodide and methanol, and not this. I suppose it is clear to you. If you have understood the mechanism, not exact mechanism here, at least the course of the reaction, you will be able to select the products easily. Let me write the answer in clear statement here. The reaction involves protonation, cleavage of molecule and carbocation formation. Since tertiary carbocation is more stable, the products are methanol and tertiary butyl iodide. You can show only the first equation for the first course. You need not show both the options. That is only for explaining. I marked everything here. You need not mark all that. You just write the protonated molecule and show these products. Only the first course of reaction, and write this statement. That would be a good answer. Now, other than the three questions I have discussed, there is another important possible question on ether, that is the mechanism of dehydration of alcohols to get ether. You can learn the mechanism. That is also another important question. Now, remember I asked you to write IUPAC name of a compound that I gave. If you have written the name, you can check with my answer now. I gave you ethyl tertiary butyl ether for giving the IUPAC name. Here, the correct name is 2-ethoxy-2-methyl propane. You know, you have to consider the longest continuous carbon chain. This cannot be the longest chain because you have an oxygen in between. So, this is the longest chain, which is propane. So, the parent hydrocarbon is propane. When this is propane, you have a methyl group attached to the second carbon atom and an ethoxy group attached to the second carbon atom. And in alphabetical order, you have to write it as 2-ethoxy-2-methyl propane. Now, I think I have done justice to the content on ethers, and I will take up some more reasoning questions in another session. Thank you.